All right, welcome to the Explainer. Today we're going to tackle something that's, super fundamental in chemistry, but honestly, it can feel like you're trying to wrestle an octopus. We're talking about balancing redox reactions.
I know, it sounds like the setup for a weird joke, right? But the answer is this incredibly powerful chemical process. It's what generates light, causes rust, and drives just a ton of reactions all around us, in nature and in industry. They're all running on the exact same engine.
And that engine? Yep, it's the redox reaction. The name itself is just a mashup of reduction and oxidation. But look, all you really need to get right now is this. It's all about electrons moving around. One thing loses them, another thing gains them. That's it. That is the absolute core of it all.
Okay, so to really get the whole picture, we've got to get to know the two partners in this, well, it's like an elegant but sometimes kind of chaotic electron dance.
So check this out. What's so cool here is how these two things are perfect opposites. You've got oxidation on one side. That's where you lose electrons. And when that happens, something called the oxidation number goes up. Just think of it like a scoreboard for electrons. Then, on the other side, you have reduction. That's when you gain electrons. And, you guessed it, the number goes down. They're literally two sides of the same coin. You can't have one without the other. No way.
And hey, if you're ever trying to remember which is which, don't worry. Chemistry's got your back with a super classic mnemonic. Leo the lion says jur. Loss of electrons is oxidation. Gain of electrons is reduction. Seriously, this one's a lifesaver.
All right, now here's where it gets a little twisty. We also have these agents. The oxidizing agent is the one that makes something else get oxidized. How? It literally snatches electrons away from it. And in doing that, it gets reduced itself. I love this analogy. It's like an agent of chaos for that other substance. And the reducing agent, it does the exact opposite. It's the generous one, the donor. It gives its electrons away, which causes something else to be reduced, and of course, it gets oxidized.
So, you might be wondering, how in the world do we keep track of all these electrons flying around, especially when you get into these big, complex molecules? Well, that's where we need to do a little cosmic accounting. And our tool for that? Something called oxidation numbers.
And assigning these numbers isn't random. There's a set of rules, a system. Pretty straightforward stuff, really. Like an uncombined atom, its number is 0. Easy. A simple ion, its number is just its charge. Makes sense. Then you've got your usual suspects like oxygen and hydrogen, which usually have a set number. But these last two are the big ones, the ones you'll use all the time. If you have a neutral compound, all the oxidation numbers have to add up to 0. And if you have a polyatomic ion, they have to add up to that ion's charge. That's the key to the whole system.
Okay, and all of this brings us to the main event, the big question. What do you do when you've got an equation where not only are the atoms all out of whack, but the electrical charges on both sides don't even match up? Yeah, you can't just slap some numbers in front and call it balanced. This is a whole different level of puzzle.
Let's take a look at a real example so you can see what I mean. On the left are reactants. We've got nitrite and aluminum. On the right are products. We have ammonia and aluminate. Now the overall charge here just happens to be the same, but look at the atoms. It's a total mess. We start with 2 oxygens and end up with 4. We start with 0 hydrogens and somehow end up with 7? How does that even happen? It's complete chaos.
So, to clean up this mess, we can't just guess. We need a system, a reliable method, and that's exactly what we have. It's called the half-reaction method, and it's brilliant because it breaks this big, ugly problem down into smaller, much more manageable steps.
So here's the game plan. First, you split the whole thing into 2 half reactions, one for oxidation, one for reduction. Then you just go down the checklist step by step. First, balance the main atoms, anything that isn't oxygen or hydrogen. Then, you balance the oxygens by adding water molecules. After that, you balance the hydrogens by adding hydrogen ions. And the very last piece of the puzzle, before you put it all back together, is to add electrons to balance out the charge on each side. It's a process, but it works every time.
So you go through all that work, you follow all the steps, and boom, you have a perfectly balanced equation. Awesome, right? Well, there's just one little problem, a catch. Our beautiful new equation is now swimming in H+ ions, and that means we've balanced it for an acidic solution. But if you remember, our problem specified a basic solution, and H+ ions, they're not really a thing there.
And this is where we get to the final, brilliant little twist in the story. This is the move that you need to know to finish the job, and it's what makes balancing and basic solutions so unique. So the question is simple. How do we get rid of those pesky H+ ions? How do we flip this thing from acidic to the basic form it's supposed to be in?
And the solution is actually super elegant. Look at this. For every single H+ ion you have on one side, you just add a hydroxide ion to both sides of the equation. That keeps it balanced, see? Then, on the side with both, the H+ and the hydroxide get together and form plain old water. The final step is just cleanup. You cancel out any extra water molecules that are on both sides of the equation. It's such a clever move. It neutralizes the acid and the whole thing stays perfectly balanced.
And with that final move, we're done. We can now write out our final, completely and correctly balanced equation. Let's see what we ended up with. Just look at that difference. Up top, you've got the chaos we started with, a total mess. And on the bottom, order, the final balanced result where every single atom and every single charge is perfectly accounted for. That right there, that is the hidden math, the hidden order that governs everything from rust on a car to a firefly's glow. Yeah, it's a bit of a process, but the end result, it's a perfect picture of how chemistry actually works. You know what really makes you think, doesn't it? This whole thing is just about finding a hidden balance, a secret set of rules that controls how these tiny little electrons jump around. So if chemistry, something that can seem so chaotic, operates on this incredibly precise system of accounting, it kind of makes you wonder, right? What other invisible systems of order are running our world, just waiting for us to figure out the rules?